Welcome, everyone, to today's Explainer. I am incredibly excited to be with you today because we're tackling one of the absolute most fascinating concepts in computer science. Before we get into the weeds, I want you to start by imagining something for me. Close your eyes and imagine you're trying to climb to the very highest peak of a massive, sprawling mountain range. The catch? You are completely blindfolded. You've got absolutely no map, no GPS, and literally no way to see the summit. How on earth do you reach the top? Well, this exact scenario is the fundamental challenge of optimization problems in computing. So let's explore exactly how algorithms navigate the dark to find the absolute best possible solutions.
So think about it. How do computers find the best answer when checking every single option is just outright impossible? Think back to our blindfold analogy for a second. Because you can't map the whole mountain, or in computing terms, search every possible state systematically because the state space is simply too massive or even infinite, you have to rely on feeling the ground directly around your feet. You can only sense what's immediately right in front of you, behind you, or beside you. You sweep your foot around, find the highest patch of dirt, and step there. This is the exact philosophy behind the entire family of local search algorithms we're diving into today.
And that perfectly sets up a core definition we need to establish. An optimization problem is essentially a scenario where the goal is simply to find the best possible configuration, what we typically call a state, without maintaining a complex search tree. Now, what does that actually mean? The absolutely crucial point here is that local search algorithms are perfectly designed for these massive or infinite spaces precisely because they throw away the map. They don't track the entire history of where they've been. They only hold on to the current state and its immediate adjacent neighbors. It's incredibly liberating for a computer's memory.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the general features of these impossible problems, then examine our first method, hill climbing. From there, we'll see how algorithms borrow from physics with simulated annealing, branch into teamwork with local beam search, and finally mirror biology itself with genetic algorithms, before comparing them all at the end. Section 1. Solving the impossible problem. Let's really set the stage for how these incredibly memory-efficient algorithms manage to tackle completely infinite state spaces without totally crashing your computer.
The absolute genius of local search algorithms lies entirely in their simplicity. Because they only maintain a single current state, they are highly memory efficient. We're talking practically zero overhead. They don't try to memorize a massive branching search tree, and they don't keep a log of millions of past configurations. They just look at what's immediately adjacent to them, the immediate neighbors, and make a split-second decision. This saves incredible amounts of computing power, making them immensely useful. In fact, sometimes they are literally the only option when you're dealing with massive or completely infinite state spaces, where a systematic step-by-step search would take until the end of the universe to finish.
Section 2. Hill climbing. The greedy approach. That foundational idea leads us directly to the most intuitive, basic algorithm in this entire family.
The mechanics of hill climbing are remarkably straightforward. It's basically a simple four-step loop. Step 1. The algorithm checks its surroundings and chooses the best immediate neighbor of its current state. Step 2. If that neighbor has a higher value, meaning if it's a step uphill, it moves to it. Step 3. That neighbor officially becomes the new current state. And Step 4. It simply repeats the loop. It continually moves in the direction of increasing value. It's essentially acting, well, greedily. It grabs the immediate improvement right in front of its face without ever looking ahead, strategizing, or planning for the future.
But here's the catch. Because it's so incredibly greedy and, frankly, blind, hill climbing has some major failure modes. First up, local maxima. Imagine a false peak. The algorithm climbs to the top of a small hill, feels that every single step around it goes down, and proudly declares, "I did it! I reached the top of the mountain!" While the true peak towers unseen just a mile away. It just gets completely stuck. Then we have ridges. Think of a sequence of local maxima creating a narrow slope. Here, our blindfolded climber just zigzags and oscillates uselessly back and forth across the ridge without making any real upward progress. It's totally inefficient. And finally, plateaus. These are completely flat areas where all neighboring states have the exact same value. The algorithm is totally lost because it can't feel which direction is up. It just wanders aimlessly. It's incredibly frustrating for our little greedy climber. Section 3. Simulated annealing. Escaping peaks. So, if our algorithm keeps getting stranded on false peaks and flat plains, how do we rescue it? How do we fix this fatal flaw? Well, we actually have to teach it a totally counterintuitive trick.
Now, what's really interesting about this is how we break the rules. We know hill climbing exclusively moves uphill, which is exactly why it gets stuck on those false peaks. But simulated annealing does something wildly different. It occasionally allows downhill moves. I know, right? Why would you go down if you want to reach the top? But to find a taller mountain, sometimes you have to be willing to walk down into the valley first. It's a brilliant, counterintuitive idea that allows the algorithm to jolt itself out of a false peak and keep exploring the wider landscape.
But where does the weird name come from? Annealing? Computer science actually borrowed this exact concept from the physical world, specifically metallurgy. In metallurgy, annealing is a physical process where a metal is heated up to a very, very high temperature. This massive heat allows its internal atoms to bounce around wildly and chaotically. Then, it's very slowly cooled down. This slow cooling allows those bouncing atoms to eventually settle into a highly structured, low-energy crystalline state. So the algorithm actually mimics this exact physical process to dictate when it makes chaotic, random moves versus precise, greedy moves.
And it achieves this using a really elegant piece of math. Don't let the formula scare you, it's actually quite simple. This equation dictates the probability of the algorithm accepting a worse or downhill move. P is just the probability. Delta E represents the change in energy, or essentially how bad the proposed downhill step is. A really bad step has a huge delta E. But the real magic here is the T at the bottom of that fraction, which stands for temperature. This single mathematical equation calculates exactly when the algorithm should risk taking a bad step, and it is heavily influenced by how hot the system currently is.
Let's break down exactly what that temperature does in practice. At a high temperature, which is the very beginning of the process, the algorithm is very likely to accept bad, downhill moves. It's bouncing around with broad, chaotic exploration, easily escaping any local false peaks. But we implement what's called a cooling schedule. As the temperature slowly decreases over time, the algorithm becomes much, much pickier. By the time it reaches a low temperature, the system is cool, and it stops accepting bad moves almost entirely. At that point, it acts exactly like our focused, standard hill climber. It perfectly balances wild, global exploration with precise, greedy climbing.
Section 4. Local beam search. Teamwork. Okay, so that takes care of getting stuck. But honestly, why climb the mountain alone when you can bring a whole search party? The entire concept of local beam search is anchored by one simple variable, k. In this algorithm, k represents the specific number of states the system tracks simultaneously. We are officially ditching the single climber approach. Instead of one lonely blindfolded person tapping around on the mountain, we now have a coordinated team of k explorers searching in parallel, generating a massive, massive boost in efficiency.
Here's how this teamwork actually functions in practice, step by step. First, the algorithm looks at all k states and generates every single possible successor for all of them at once. This creates a massive pool of potential next steps. Step 2. If any of those successors in that pool is the absolute goal, the search stops. Boom, we won. But if not, we move to step 3. It selects the k absolute best successors from that entire massive pool and repeats. It's essentially a pretty brutal game of survival of the fittest. The best paths are shared among the team, and any climbers who are stuck floundering at the bottom of the mountain are instantly abandoned, so the system can focus all its memory on the most promising routes.
But, as always, there's a flaw here too. Standard beam search always selects the absolute best k successors. Because of that rigid rule, the entire team can quickly flock to the exact same false peak, crowding together and totally losing all their exploration power. They just bunch up. To fix this, we use stochastic beam search. Instead of just coldly taking the absolute best, it chooses the k successors randomly, but with a probability based on their fitness. By injecting just a little bit of randomness, the team maintains its diversity and spreads out across the mountain range, rather than crowding like sheep on one single bump.
Section 5. Genetic algorithms. Natural selection. Now, for our final leap. We are moving from physics and basic teamwork into pure, undeniable biology. What happens when algorithms don't just work together, but actually evolve?
Genetic algorithms, or GAs, lean heavily on biology. They're actually a really fascinating variant of that stochastic beam search we just talked about, but they're directly inspired by natural selection. Instead of a team of climbers, the algorithm maintains a population of individuals. And these states are often represented as finite strings, like lines of binary code, which act exactly like digital DNA. And just like in evolutionary survival in the real world, we use a fitness function to evaluate the environment and determine exactly how good or fit a specific state is to survive. This creates an actual functioning evolutionary loop. Step 1 is selection. Individuals are chosen for reproduction strictly based on that fitness function. Only the strong survive. Step 2 is crossover. The chosen pairs literally mate by chopping up their data strings and combining portions of them to create entirely new offspring solutions. You take the first half of parent A and the second half of parent B. And finally, step 3 is mutation. The algorithm randomly flips a bit or changes a tiny piece of the string to ensure the population doesn't lose genetic diversity. And this brilliantly illustrates how borrowing from biology, literally chopping, mixing data strings, and mutating bits, creates uniquely powerful, highly evolved offspring solutions over thousands of generations.
Section 6. Comparing search strategies. We've covered an incredible amount of ground today, transitioning from a simple blind climber all the way to a full-blown digital ecosystem. Let's put everything we've learned into one simple, satisfying picture.
Let's trace the exact evolution of the algorithms we discussed today. We started with hill climbing. It had a state memory of just 1, moved strictly and always uphill, and its only goal was to reach a maximum, which, as we saw, often got it stuck. To fix that, we moved to simulated annealing. Still just one state of memory, but it allowed stochastic, downhill moves to escape those tricky local maxima. Then, we expanded our memory. Local beam search tracks k-states, searching in parallel to find the best of multiple paths. And finally, genetic algorithms. The memory is an entire population. The movement style is crossover and mutation. And the ultimate goal is digital evolution toward perfect fitness. It's just an absolutely incredible progression of problem solving.
I want to leave you with this really provocative thought. We've seen today how deeply mathematical, purely digital algorithms rely entirely on the physical world, from the cooling of molten metals to the biological evolution of DNA, for their inspiration. By borrowing these natural concepts, computers can literally solve problems that are far too massive to calculate directly. It really begs the question, what other hidden systems in nature are out there, just waiting to teach computers how to solve the unsolvable? Think about that for a bit. Thank you so much for joining me on this explainer. I hope this really illuminated the path for you, and I will catch you next time.